Okay, so good morning, everyone. Thank you for coming to my talk today. Glad to see so many of you here, despite of the strike today. Hope you all get home today. And yeah, so I'm going to talk about some mechanisms we have applied to our research code, VirtualFluids, trying to make it more towards sustainability. Let's get right into it. I want to start with a quick introduction to the code. So VirtualFluids is software doing computational fluid dynamics. It's based on the Let's-Boltzmann method. It's basically doing turbulent or solving turbulent and multi-component flow problems. It's not only the solver, it also contains a lot of functionalities around regarding grid refinement, grid generation, and post-processing capabilities. It's developed at my home institute, the Institute for Computational Modeling and Civil Engineering. And nobody knows exactly, but my approximation is that it's 25 years old, or at least the first development starts 25 years ago on a software which was then later be called VirtualFluids. So in this regard, it has been the base for some generations of PhDs in this time period. It's mainly written in C++. It has CMake-based build system that's pretty standard in the C++ world. It also contains some CUDA files, some Python code, but it's mainly C++, and it's basically 125,000 lines of code. So just to give you a feeling about the size of the project. Traditionally, the software was implemented on Windows computers by the researchers in the past, and usually it's then ported to Linux to run it on HPC clusters. So in this regard, we are supporting at the moment GCC and Clang, and also the MVC compiler. In principle, it also compiles on macOS, but and actually it's pretty fast with the M1 chip, but because of the fact that macOS does not support NVIDIA graphic cards anymore, we cannot do the simulations on GPUs. That's quite unfortunate. And so as I already mentioned, the things we are doing can be quite compute intensive. So we have to make use of high performance computing and utilizing multiple GPUs, and also running our simulations on distributed CPUs. So VirtualFluids is pretty much what you would expect from such an old research code. So when I joined the team 4 years ago, I was faced with a lot of technical debt, I would say. So it's not unusual, I would say. So there was a lot of duplications and unmaintained code. A lot of things which we were able to do in the past, but we cannot do it anymore. And pretty usual stuff, but so we were lucky in Braunschweig that we got a project called ShieldSoft, a project for sustainable research software where different people from different fields came together with their research code and discussed their problems and trying to find common solutions based on the technologies you all know, which are quite established in the research, or not in research, but in software engineering community, like continuous integration and virtualization. So when I joined the team, there was already a version control. That was nice, but there was no CI. So the first thing I did was setting up CI pipelines containing build stages or compilation with different configurations. We also enabled after some time that we do not allow new warnings in the code. It was quite a fight, which is also sometimes annoying for the researchers because they do their changes and they push their changes to the repository, and then pipeline is failing because there are new warnings in the code. And so we also do quite some testing and code analysis. I come to this on the next slide. And we also have documentation pages created with Doxygen, because there was always Doxygen in the code. So Doxygen is some in-code documentation. And we deploy this to GitLab page together with some wiki-like documentation pages. So knowing that the code compiled is nice, but what you actually want, of course, is you want to know if the code still does the things it is supposed to do. So we have different kinds of tests implemented in VirtualFluids. There are unit tests based on Google Test. Unit tests are nice. They run pretty fast. Number of tests is growing, but some people are more used to write unit tests than others. So some people are not so motivated writing unit tests, and it is, even for me, sometimes also very hard writing unit tests when it comes to the numeric parts. So often you are not able to isolate your parts from others, so you can only test it all together, so that's why it's hard writing unit tests. So we come up with a second layer of tests, we call this regression tests. Regression tests are pretty simple a way of testing the code. It's basically just you run your simulation, or you create a setup for your simulation, and you validate your data, your results, with however, experimental data, or just by watching at the data. Then you store this data in some other reference repository, and then you can repeat your simulations and simply compare the new computed results with this reference data. And this is pretty easy for everyone, so we now have some kind of this policy that if there is a new feature in the code, that at least there should be a regression test to make sure that we can still do this new feature also in the future. And yeah, so unit tests are pretty fast, as I said, so they are executed as much as we can. Regression tests usually are executed every night. We also have some HPC tests. So we're utilizing a tool, HPC Rocket, which connects from the continuous integration pipeline to HPC cluster using SSH, copying some data to the cluster, submitting the Slurm script, waiting for the results, and copying the results back to the CI pipeline. And yeah, so we have some HPC tests. They are usually executed every week, and some tests are only executed manually. And yeah, we also do some performance testing, but it's not very advanced. Okay, then we also do static code analysis. Static code analysis is pretty low-hanging fruits for every project, I would say. So there are plenty of nice tools out there. You just can take them and integrate them in your CI pipeline. So for example, we have CPP-Check and ClangTidy integrated, C++ static code tools. Then Lizard is a nice tool I highly recommend. So it's language agnostic, and it calculates the cyclomatic complexity of your project. So you can take this and you easily find parts in your code which might be too complex and where it maybe makes sense to split this up into smaller parts to make it more readable. GCOV for code coverage, and also sanitizers are integrated. Yeah, as I said, we have these jobs integrated in our continuous integration pipeline, and then we do another step. We deploy these results on a self-hosted SonarQube server. We have SonarQube. It's basically a visualizer for this quality results, and it's free if you want to host it by yourself. And yeah, this is what we did, and then researchers can take a look on their latest changes and have basically a visualization of these static code analysis results. So for example, here on the right, we have a comparison which is always true. This is probably a bug, I don't know, but then you can take care of this. Of course, we also do virtualization. Virtualization is the base for continuous integration. In this regard, we created a development container for VirtualFluids, which is stored on the GitLab registry. And we are also having a workflow with VS Code. So it's pretty nice. I really love this. In the past, it was really a pain getting started with the project. And you have to install so many dependencies on your computer, setting up environment variables and whatsoever. Really a pain. And now with the development container, the entry barrier is really low. You just need Docker, pull the image from the registry, and getting started with the dev container. For those of you who don't know, dev container is an extension for Visual Studio Code where you can where Visual Studio Code connects to the Docker container. So you can develop your code directly in the Docker container, so it's pretty awesome. Yeah, and also, we have also some experience doing Singularity on HPC systems. All right. So we have established a workflow then in our institution. We switched from an internal repository to the university repository. So this is publicly accessible. It enables us also working with external developers, where we have a few, just very few. Yeah, and we came up with a solution where we have a public repository on the GitLab server, and we are working with a forking strategy. This means everyone has to fork this public repository. The reason for that is that people sometimes want to develop in private. Yeah, I don't know why they are scared. They don't want to exchange the latest changes. And so with this strategy, if this is possible, they can make their forks private. And then if they have something ready, they can create a merge request and get their latest changes back into the main repository. We have two branches, main and develop. So develop is the branch where all changes sums up, and then once in a while, we merge back into the main branch, create a tag, and create a publication out of this. So that's then the last step. By the way, we are doing this since December last year, so it's a pretty new process. So far, we are in version, I don't know, 0.1 or something like this. Yeah, so when we have the main tag created, this is then mirrored to the GitHub repository. So we have a GitHub repository. Yesterday, where there were a couple of talks discussing developing on GitHub and then mirroring to GitLab. We do it this way. We mirror to GitHub, the main branch and the tag. The only reason for that is that we want to make use of this nice feature from Zenodo, the integration of the publication. So if we create then a release on Zenodo, on GitHub, thanks. So yeah, main branch and the tag are mirrored to GitHub, then we create a release on GitHub, and then this triggers an automatic release on Zenodo. This is pretty nice. We also have a CFF file in the project which contains the metadata, so you basically have to do nothing despite you only have to create this release. All right, so with that, there are a lot of nice tools out there. Just use this. Having CI and having containers is pretty awesome, but you really need, or at least my experience is, you really need to have tests to really make sure that your code does what it should do. And the last thing, all this, it's my personal opinion, all these things, continuous integration, containerization, everything everyone is talking about, is really awesome. It really brings value to the project, but it also always brings additional complexity to the project. And you have to maintain this complexity, you have to handle this, and you need people for this. And I asked myself the question, what happened when I leave, for example, this institute? So most of the things I showed to you are implemented by myself. And I have the hope that this will continue, but never be sure. So I don't know. So yeah, finger crossed that this will continue and that there are still people who see the benefits of all that stuff. Okay. So thanks.